All right, well, in this video, we're going to talk about conclusions. That is, how do we write up the results of some of these analyses? So one of the first things that we have to talk about when we talk about conclusions is the idea, concept, meaning of statistics. Of significance, statistical significance. So in a hypothesis test, when we run these, we can either reject the null or fail to reject the null. Remember, we never accept the null hypothesis. And one way that you can think about this is like a court case. In a court case, we assemble evidence to try to declare someone guilty or to try to defend their innocence. But when the conclusion comes, we get a verdict of guilty or not guilty. There's no verdict of innocent. And that's because we don't know. It wasn't on the person to prove their innocence. They just kind of had to sit there and somebody else had to prove them guilty. This is the same thing with the null hypothesis. The null hypothesis doesn't have to prove itself. It just kind of sits there, and then we, as the researcher or the data, are trying to present a case where either there is enough evidence to reject the null hypothesis or there's not. But again, the null hypothesis isn't proving anything in our research. So really, when we are looking at the null hypothesis, because it's never trying to prove anything, it can never be accepted per se. There's a whole technical aspect here too, and we're kind of skimming on the surface. But for me, actually, a court case is a really, really, really useful generic analogy for null hypothesis statistics testing. And it has a lot of extensions. In fact, we may come back to it in a future chapter. So if you reject the null, again, this is statistical significance. So when we say a result was statistically significant, what we mean is that in a statistical null hypothesis test, we rejected the null hypothesis. And so because all of those tests have an associated alpha level, when we say statistically significant, technically it's statistically significant at that alpha level, because recall, if we change the alpha level, the p-value may be above or below the new alpha level in a different way. So it may not be clear if we change the alpha level. But typically when we say statistically significant, then it's at a alpha level of 0.05, because that's what everybody uses. So one example you might see this in is there was a statistically significant difference in relationship. And what ends up happening is that in applied research, people just say there was a significant relationship, and they kind of drop the statistically part of that. So there was a significant relationship, or there was a significant difference between a couple groups. So what is statistics? Or what is statistical significance? First of all, let's talk about what statistical significance is not. Statistical significance is not practically meaningful. And this is so important. Actually, this is a huge thing when interpreting applied research. Whenever someone says it's significant, I kind of raise my eyebrows and say, yeah, but is it really? Because statistical significance, quite literally, this is not like some technical distinction. Statistical significance does not imply practical meaning. Now, is something that's statistically significant more likely to be practically meaningful than something that's not? Yes. But in the same way that correlation isn't causation, and it's more like correlation is not sufficient for causation, it's the same kind of idea for statistically significant. It's not that statistical significance isn't practical significance, and that's a true statement, but it's more like statistical significance is not sufficient for practical significance. So if I have a correlation, it could be causal, but it could not. If I have statistical significance, it could be practically meaningful, but it could not be. And in fact, this is why I will be a stickler about the use of statistical significance rather than the more ambiguous and confusing term of just significant. So it's really easy to say there was a significant relationship. But significant relationship kind of implies that it's a meaningful relationship. After all, isn't that what the word significant means? But the term statistical significance is kind of a buzzword, almost a pronoun, statistical significance. that implies a very, very specific mathematical relationship. Specifically, that after calculating a test statistic, it fell within the critical region of a null hypothesis of a distribution that was specified by the hypothesized distribution of the statistic under the null hypothesis. And that's not what most people say when they mean it was a significant relationship. And it's why it's important to be precise. So when I talk about a statistically significant relationship, I tend to say the relationship is statistically significant, and to use that full term to try to help clarify. Now, even when you clarify, again, most lay people don't understand that clarification, but at least scientists are more likely to understand. Of course, if you say a significant relationship to scientists, they also tend to understand that you're implying statistical significance, not practical significance. But as a field, many fields have actually run into trouble on this, and so there's becoming more intention from the statistical community about specifying whether it's statistically significant or practically significant or both. Now, statistical significance, just like it's not practically meaningful, it also doesn't mean that something is bound to be repeated in a future experiment. So if I find that something is statistically significant at the 0.05 level, there's actually a really cool paper out indicating that the chances of repetition are astonishingly low, very surprisingly low, and that you have to be statistically significant. Your p-value has to be like 0.001 to have a 95% chance of repeating the effect under some hypotheses, or even smaller. So statistical significance does not mean that a future experiment will repeat the results that you've found. That's not what it's saying. It's not even saying that a future experiment will also be statistically significant. So that's not what statistical significance is about. It's not about repetition. What statistical significance is a connection to the null hypothesis. It says that the data are unlikely under the null hypothesis. So this is important, but realize that the null hypothesis is a very specific value, very often 0. So if we say the data are unlikely under the null hypothesis, this could be saying that mu equals 0 is unlikely, but mu equals 0.01 is very likely. And that's why one of the ways that we can get something that's statistically significant but not practically significant is if the difference is 0.01, this could be a statistically significant difference from 0, but not a practically meaningful difference. This especially happens when we have a ton of data. The other thing statistical significance really talks about is evidence of relationship in the population. So it's indicating that we are likely to see this if we redid the experiment. And the relationship to the population, as we mentioned earlier, is the big thing. It's why we really like statistics, is it lets us take a sample and then discuss evidence of relationship in the population. Now, the relationship, we're just saying that the relationship isn't 0, so the relationship is there. Could be a very, very small relationship, but it is evidence that there is a relationship there in the population. So what we're really doing here is determining, when we talk about statistical significance, is we're looking at the sample and we're determining if we just got lucky picking the sample. And so that's the size of the effect we saw. It was just, there actually wasn't anything going on, null hypothesis. There wasn't a mean difference, but we kind of got lucky when we picked the sample, and so one group was bigger than the other. So just kind of this random noise. That's what we're doing when we determine significance. We're seeing if it was luck, or we're seeing if there's enough evidence to determine that it really is more likely to be an underlying trend in the population. And we want to be kind of hesitant before making that claim. So we define, quote unquote, more likely that there's a trend in the population to be that we think there's only a 5% chance or less that it came from the null hypothesis. And really what that p-value is implying is that there's a p-value proportion chance that in a future experiment under the null hypothesis we would see at or more extreme of a statistic. So again, this is what significance helps with. It helps us determine if there's a relationship in the population, or if that's a more probable case than there not being a relationship in the population. But you'll note it says nothing about the size. So the size of a population is still up for debate if we're using hypothesis testing. And this is where confidence intervals are extraordinarily important, because confidence intervals let us get a feel for what a reasonable size of the effect might be. Something else called effect size can be helpful here too. So significance is not enough. When we're making conclusions, stating that a relationship was significant is just, it's not enough. It's not enough to really describe or give a takeaway to a reader when trying to summarize your results. Think about well, I'm sorry. Let's look at a couple bad conclusions. So, and this is assuming that we had statistically significant results. So, and these are things that people have actually written, by the way. This is not just making it up, but this is like the bottom line. People write their conclusions and they say this and nothing else. So the results are significant. Something is statistically significantly different than something else. Oh, that's pretty good. And actually, it's not pretty good, but some students think, hey, this is the be all end all of answers. I just replace A if I'm feeling really, really like a great student. I replace A with the variable name for the first variable and B with the variable name of the second variable, and then I'm an amazing student. Isn't Dr. Florin going to be so impressed with me? Or we rejected the null hypothesis, or we failed to reject the null hypothesis, or if you want to fail my class, right, we accepted the null hypothesis after I have in big bold letters, never accept the null hypothesis. So these are all bad conclusions, and they're bad conclusions because they're missing a few key factors. To think about intuitively, and we'll talk about what these are in the next slide, but to think about intuitively, what are these missing? And again, it's the problem is that people write these and nothing else. But consider if you just did a research study and then you took this explanation to a member of your family. I use a little brother or a little sister. Whether you have one or not, it's a great mental example of a layperson who doesn't really understand statistics. And let's say I went to my little brother and I said, the results are significant. Would they have any clue what you mean? Better yet, we rejected the null hypothesis. Period. Nothing else. Would they have any clue what that means? And the answer is, of course, no. They would have absolutely no clue what that means. If I said the results are significant, you wouldn't think statistical significance, you'd think meaningful if you aren't a statistically minded person. Even if I said A is statistically significantly different than B, yeah, what does that really mean? I mean, does that tell you is A better than B? Is A worse than B? What does statistically significant mean? I mean, these conclusions are bad, not because the words themselves should never be included in the conclusions, but because they lack a lot of context. And if you just end here, again, think about if you told your little brother or your little sister hypothetically this, they would just kind of stare at you and say, okay. So how do we conclude? Well, we add some context and interpretation to these statistics. So typically we hit a few different components. What test was used? So it's kind of important to talk about what the test is. What were the results? Now this is kind of something that is a little more bland. I'm going to use the word bland. It's a little more bland. We'll see in an example in a sec. It doesn't really require much explanation, but is important to state so that people can understand what happened. Now, I will say what the results were. This little component is something that changes with every analysis. So in a t-test, I'll tell you what the t-statistic was, the test statistic was. In a chi-squared test, I'll tell you what the chi-squared statistic was. In a correlation, I'll tell you what the correlation was. So this is going to change every test we use. And then you have to close when you're concluding statistics research, when you're writing your conclusions. You have to say, what does this mean? What does this mean? And because you have to talk about what this means in a way that actually explains to somebody what this practically means, it's going to take a lot longer than just writing "this is significant" and assuming that it hits all of these different things. Again, consider if you had to explain this to a little brother or sister, you can't do it in 5 words or less. It's going to take you a little bit of time to kind of explain all the different pieces. So in interpreting what statistics mean in a conclusion section, written descriptions are helpful, but they're not the only things that you can use. Graphics and tables can often be as much or more help than a textual description, so use them if they help you illustrate your point. Again, think that you're trying to explain this to a younger sibling, and think about what's going to help you get your point across. In the same way, reporting a confidence interval can be really helpful in determining like a reasonable range of conclusions or a reasonable range of sizes of your effect that you have seen. And there's multiple ways. In fact, I'll show an example of how do we do conclusions with a p-value and with a confidence interval and demonstrate how the confidence interval actually adds a little bit more information than just the p-value. Both of these are things like you may see in a professional journal or a professional style write-up. And both are, but because of that, you shouldn't feel like one is necessarily better than the other. So how do we conclude using a p-value? And again, note that this is quite a bit longer than the results are significant. So I'm describing a bit about the population of the first sentence. So this is, what did you do? I ran a Pearson's correlation. What did you find? Well, I found a strong, positive, statistically significant linear relationship. So this is a description of what the relationship is. And again, note that this is so much more than statistical significance. It describes the strength, and this is the effect size. You can kind of Google different effect sizes for different statistics to determine weak, medium, strong. Positive. Well, we learned in Math 115 and 116 how to identify positive and negative correlation. So I'm indicating that this is a positive correlation. Now, my client or my reader may not know, my little brother's not going to know what a positive correlation is, but this is part of the results. I did find one, and maybe I have to go and explain that because they're not going to know what that is. So here's where I'm kind of explaining, not in statisticalese per se, but I'm not hiding away from statistical language. Strong, positive, statistically significant linear relationship. This is a little bit technical, and I'm including some of my technical details. I'm including my p-value. I'm including my statistic that's meaningful. And you can look up in whatever reporting guides you want. I tend to use APA, but you could use MLA or however you'd like to write these up, how you report particular statistics. So for instance, if I were reporting a T statistic, typically it's reported as T and then parentheses and then the degrees of freedom inside the parentheses equals and then whatever your test statistic was that was distributed as a T distribution, and then you have your p-value after that. So this last sentence is really where I want to write the take home of what does it mean. So I want to transfer from this a little bit more technical language. And again, note here, I'm being very descriptive and very straightforward about what it was and what happened. I'm not hiding behind it was significant or something very generic and undescriptive like that. But I'm also not hiding away from technical language such as a positive relationship, a statistically significant relationship. It was a linear relationship. It was a strong relationship. There's a whole ton of description here. But my little brother may not know what that means. So what does that mean? Well, this means that we have evidence that for the whole population, and again, this is what statistical significance means. So if I'm explaining it to my little brother or sister, they don't know what statistical significance means, but I know that a statistically significant result means that it connects to the whole population. I have evidence that this is true for the whole population, not just for my sample. That's the meaning of a statistically significant result. So interpreting statistical significance to say that we have evidence that in the whole population, higher weights are associated with higher heights. Well, this is just a basic description in my context of what a positive relationship means. So higher weights are associated with higher heights. Again, I'm just describing how this plays out. Now, I'm noting that this is vice versa because, again, correlation is not causation. I don't know if higher weights are associated with higher heights or higher heights are associated with higher weights. Also note that I'm using the word associated here. I'm not using causal. It's not higher weights cause higher heights. Wouldn't that be funny? Or higher heights cause higher weights. I'm just indicating that they're associated with one another because this is observational and I don't have enough information to determine causation. So again, think about this explanation. Now, if you told this to your little brother, would they have any clue what you mean? And hopefully, even though they may not understand the details here, this last sentence for them really clarifies kind of the takeaway, gives them something to walk away with in interpretation. So for the whole population, I have evidence that higher weights are associated with higher heights. And you know, instead of and vice versa, I could say or maybe vice versa, indicating that I don't know which one's which. But this gives a much stronger takeaway than, again, some of those previous things on there was a significant relationship or I rejected the null hypothesis. This is much closer to what we're looking for. Now, I'll say that the p-value conclusion just talks about statistical significance. It does not conclude regarding the strength of the population relationship. As we said before, statistical significance doesn't speak to strength. It just speaks to the fact that we have evidence that it's not zero. So we could fix this by providing a confidence interval, and a confidence interval would let us speak a little bit more directly to the strength. So how would we do that? Well, if I wanted to conclude using a confidence interval, and again, you don't have to do this every time. In fact, most of my conclusions tend to look like this, not using a confidence interval. Confidence interval is becoming more in practice in statistics, but both of these are still very widely used. So for a confidence interval, I might have a very similar statement. In fact, I think everything through here is identical. The only difference is that instead of a p-value, I have a 95% confidence interval. Now you can remember from your previous studies that a 95% confidence interval can function for hypothesis tests. If I'm testing the null hypothesis that the correlation is zero, then I would look in the confidence interval to see is zero inside the confidence interval. If the null hypothesized value is in the confidence interval, I fail to reject the null hypothesis. If the null hypothesized value is not in the confidence interval, I can reject the null hypothesis. So because zero is outside of this confidence interval, it's clear that this is a statistically significant relationship. And again, I list this in text. Now note that I can also add, in addition to the fact that I have evidence for the whole population, again, statistical significance, I also have evidence that the higher weights are strongly associated with higher heights. So previously I just said that they were associated, that there was a positive association, and that was true based on the previous statistic with just a p-value. But now that I have a confidence interval, I'm able to indicate the reasonable range at which the size of the effect would be. Now, I would expect the size of the effect for a 95% confidence interval, the true population size of the effect, to be between 0.7 and 0.89. Both of these are very high correlations depending on the context. So for both of these, this is indicating a strong relationship. Even if the value was at the lowest possible reasonable expectation of 0.7, this is still a strong relationship or a strong association. And because of this, I can be confident in the strength of the relationship because even the lowest hypothesized relationship in the confidence interval is still pretty darn strong. So here I can make a conclusion that I couldn't make with just concluding in my p-value, specifically that the higher weights are strongly associated with higher heights, whereas in the previous write-up I just said higher weights are associated with higher heights because I didn't want to assume that statistical significance is the same thing as practical significance, and it's not. Now, I will add one thing here. I know we've talked about statistical and practical significance, but just one more thing to add on here is that very often non-statisticians think that the lower p-value you have, the stronger the relationship is, and that is not true. The strength of the relationship is indicated by the size of the relationship, not the p-value. The p-value is just the probability, again, that you would observe something that strong or stronger under the null hypothesis. Now that probability is heavily influenced by the sample size. So one of the things that you'll often see is if I have a sample size of 1,000,000 plus data points, my p-values are going to be extraordinarily low, even if the size of the effect is also pretty low. So I am really, really, really careful about this, especially when I have a high sample size, that it doesn't really matter how big my p-value is. I really want to look at the effect size to determine the size of the difference. And again, I can use a 95% confidence interval on my statistic of interest to determine that. So this would be the mean difference in a two-sample t-test. Chi-square doesn't really have something like this. We'll talk about an equivalent when we do the programming section and jump into R. And then for the correlation, it'd be a 95% confidence interval on the correlation coefficient. So I'm not going to continue on this too much. This is kind of the maybe one of the few times we'll talk about it in the course. But I will say that another thing that we can do is determine strength of the relationship by calculating an effect size. Now in correlation, it's kind of handy because the correlation coefficient is itself an effect size. But effect sizes or standardized effect sizes that many people use aren't part of the statistical calculation in other tests. That said, these are not particularly difficult to find or to calculate. Simply Google effect size for a t-test or effect size for a chi-squared or something like that. And then if you're looking to determine, well, is this a big effect size, a small effect size, etc., just do a second Google search for rules of thumb for interpreting a Cohen's d effect size or rules of thumb for interpreting a Glass's delta, etc. We do talk about these, just not really in this class. So if you take regression, if you take an ANOVA class, if you take some of the non-parametric stuff, we'll talk a little bit more in depth about effect sizes, how to calculate some of them, and the interpretations that you can walk away with them. All right. So to close out, let's talk about what happens when results aren't statistically significant. So I just did a test. My p-value is like, I don't know, 0.5, whatever. Your p-value is above 0.05. So the results aren't statistically significant. What now? First rule, big, bold letters, do not accept the null hypothesis. And this is surprisingly easy to do in conclusions. Even if like you mentally know, sometimes you'll catch yourself saying, well, there wasn't a difference between the two. And that's accepting the null hypothesis. Note that if I'm comparing two groups and the null hypothesis is that there's not a difference between the two, if my conclusion, when I don't find a statistically significant difference, is that there's not a difference between the two, then that is accepting the null hypothesis. So maybe jot that down on your notes. You know, I hope you're taking notes on what I'm saying, not just what's in here. But that might be a big one to make sure you jot down in star is, just put a quote next to this, don't accept the null, and say, an example of accepting the null would be something like, there wasn't a difference. And that is accepting the null hypothesis. And again, it can really sneak up on you, especially in the conclusions. And so going into this, again, not accepting the null or the results not being significant does not mean that there's no relationship. All that it means is that we didn't have enough evidence to conclude that there was a relationship in the population. Now, I will say that all of this is about population. It is very likely that you found some kind of a difference in the sample. In fact, mathematically, if you had a truly continuous variable, it's impossible that your two sample means would be the same if you're doing a two sample t-test. So don't try to don't try to bend your mind into pretzels to get this. It's really quite simple. The statistical conclusion is about the population. The sample statistics you found are about the sample. So you can have a sample mean that's different, and it cannot be statistically significant. So that means that even though the means were different, that sized difference wasn't enough to determine that there was a good chance of it being different in the underlying population. So even if you didn't find enough evidence to conclude there was a difference in the population, You probably did have a difference in your sample, and that's okay. Again, the whole point of this is to say, did we just get lucky with the sample, or does the sample give us enough data to determine that there really, really is a difference? So for the p-value approach, for a non-significant conclusion, it's pretty straightforward. We kind of do the same thing, introduce the analysis, but then we just say we did not find a statistically significant linear relationship. And so I'll have a lower correlation, of course, and then my p-value is going to be above 0.05. And this means that we don't have evidence that the whole population, higher weights are associated with higher heights. Or vice versa. And here we don't have evidence that there was any association. So I should say, instead of just higher with higher, which would imply a positive relationship, I should say that we don't have any evidence that weight was associated with height and not qualify that with higher weights and higher height. So that might be even a little bit better of a way to say this conclusion section. And note that all this is phrased very, very similarly. And again, it's done so to avoid the common pitfall that people make, which is to say there wasn't a relationship between weights and height. So very, very, very often students will end with, we didn't find a statistically significant relationship. This means that there was no relationship between weight and height. And that is not true. That is not true. First of all, in your sample, there's probably evidence of at least some kind of relationship between weight and height. So for the sample, that's not true. So make sure you're talking in your conclusions about the whole population, because that's what the statistic is testing. But then furthermore, we're not saying that there's no relationship between weight and height in the whole population. I don't know if there is or not. I'm just saying that in our study, we didn't have evidence to support that conclusion. And that's a very, very, very different style of conclusion. So be careful about this. This is an issue that students do run into, and I don't want you to be one of the students who runs into this. So make sure that as you're writing your conclusions here, whether they're significant or whether they're not, you're being clear about the nature of the relationship and just saying we either have evidence that there's a relationship or we don't have evidence that there's a relationship, and never making the statement there is evidence that there is not a relationship, or because we didn't have a statistically significant relationship, that means that there is no relationship. All right, so as a final slide, well, what can we conclude when there's non-significant results? And this is a tough thing. I mean, because there's actually not a lot of conclusions that you can make when the results are non-statistically significant. And it's why accepting the null is so tempting, because everybody wants to say, oh, well, I didn't find a relationship, so that means there's not a relationship. In fact, I'm working with very many high-profile researchers right now. I'm working on some fun research teams, and they all fell into this trap. They're all talking about how, oh, because we didn't find a relationship, it's so interesting that there's not a relationship between these. And that's not the conclusion that we can take away. We have to say we didn't have evidence to determine a relationship, and we have to avoid saying we found that there wasn't a relationship. Those are two very, very, very different statements, one of which is supported by our data and one of which is not. And again, it's not that we physically can't write or say the words, it's that are the words supported by our statistical analysis and by our data? And one of those statements is supported and one is not. The results could be due to chance, and that's kind of the reason that it's tough to make any claims, because the results could just be due to chance. Ultimately, it means that the populations could just be a chance draw from the null distribution. Now, it's important to note that this is always a possibility. Even if we had a very low p-value, it's always a possibility that these results were due by chance. What we're saying when the results are non-significant is it's reasonable enough that they're due by chance that we don't feel comfortable going against that claim. And the results being due by chance is another phrasing of the null hypothesis. So what we're saying is that this is reasonable enough of a claim that we don't feel like we could have evidence against it. Just like when somebody says, I'm innocent, if we don't have enough evidence against them to prove that they're guilty, the claim of being innocent is a reasonable enough claim so that we have to let them go free. Now, the issue and with accepting the null hypothesis is, though they could be due to chance, results could also be due to a real effect. And this is why we can't accept the null, is because we don't know. We don't know if the results were due to chance or due to a real effect. And actually, it'd be really nice if we could say these results were just due to chance, because then we could accept the null. But that's not the case. And this is why non-significant results are always so disappointing for so many people that we work with, is because they really didn't tell you anything other than that you didn't have enough evidence. I mean, they don't even tell you that what you were testing or hoping for is not true, because again, they don't accept the null. We don't know if the results were due to chance or to a real effect. Now, effect size is actually a big piece when results are non-significant, because there's an interesting thing that happens with non-significance if we also have a large effect size. Now, this phenomena really only happens when we have small sample sizes. But if we have a non-statistically significant statistical test, but a large effect size, this mix actually implies that maybe we should do another study, because if we have a large or practically meaningful effect size, even if the results were non-statistically significant, that means that hey, there could actually be a large effect here. We just didn't have enough data to determine if that's true or not. So let's run this again and get more data to make that determination. Now, it's not just the effect size of what you saw, but it's also the confidence interval of the effect size. So a 95% confidence interval is useful here because it tells you what are the reasonable effect sizes that could be there. And if anything is interesting in that confidence interval, like the peak of that confidence interval, the bottom of that confidence interval, looks like it could be an interesting or practically meaningful effect size, then the same suggestion would apply. Hey, you should redo this study. You should get a higher sample size that's going to increase your precision, so that you can determine, is that the size of the effect, is that meaningful or not, and you'll have enough sample size to determine that such an effect exists or doesn't. Now, if the effect size is small, so let's say we did a 95% confidence interval, the ends of that confidence interval and everything inside of it is too small for us to care about, then this is less important and less meaningful. But it is something to consider when you have non-significant results, especially for clients, because they always get so disappointed when we have non-significant results and they feel like they have nothing to do. So that's a bit of a consideration that you can make and help them walk through. So this has been a discussion, a bit of a long discussion, I apologize, but on how we write conclusions, how we do and don't write conclusions. I apologize for the length of this video, but it is really, really important content, and it's something that I see students make mistakes on all the time. So I hope this was helpful, and hope that as you're writing your conclusions, this is going to be helpful in figuring out ways to do it and ways to not do it. So I think our next video is going to be how to run some of these analyses in R, and then we get to start lecture 1, the end of review, where we actually get going in designing these experiments that let us make causal claims.